Let's take a look at this example problem where we are going to set up and actually evaluate a triple integral in spherical coordinates. So let r be greater than 0. We won't specify it beyond that in this problem. Consider this triple integral, which is currently written in rectangular coordinates. What we're going to do is first take a few minutes to visualize the domain of integration, because I think when you're first learning spherical coordinates, it's hard to see what this is. In fact, it could be hard to see what it is, even if you've been doing spherical coordinates for years. So we will visualize this in XYZ space, and then we will reinterpret the domain of integration in spherical coordinates so that we can set up this integral in spherical coordinates, and then we'll go ahead and evaluate it as well. When I am trying to understand the domain of integration for a triple integral, I recommend first looking at the outer bounds, because that's a two-dimensional domain, and it's what I like to think of as the shadow that the domain of integration casts on what is in this case the xy plane. So we'll start by drawing what the outer bounds are communicating about the xy coordinates. Okay, so here's the xy plane. Keeping with this theme of working with the outside first, let's first look at the outermost variable and its bounds of integration. So y goes between two constants, which it always should for the outermost bounds of integration. Y is going to go from negative r up through positive r. So I'm going to sketch two horizontal lines, one at negative r and the other one at r. So the shadow for our domain of integration is going to live between those two horizontal bands. Next, we take a look at the middle bounds of integration. X is greater than or equal to 0 and less than or equal to the square root of r squared minus y squared. X equals 0 is the y-axis. So this is telling us that our shadow lives to the right. So what we'll sketch will be over here. If you don't see it right away, I recommend taking the expression x equals square root r squared minus y squared, writing it down, and seeing what happens if you square both sides. So x equals the square root of r squared minus y squared means that our x values satisfy the equation x squared equals r squared minus y squared. That's the circle of radius r. So we could write x squared plus y squared equals r squared. I'm going to point out here that it's not going to be the entire circle, because when you say that x is a square root, that tells you that x is greater than or equal to 0. So the equation x equals the square root of r squared minus y squared is not the entire circle of radius r, it's a subset of it. In fact, it's the right semicircle. So let me add that to our picture. Okay, so here's our domain of integration, or rather the shadow that it casts in the xy plane. It's like a right semi-disk. Now to get the three-dimensional domain of integration, I'm going to take the xy plane and resketch this picture, but as a subset of xyz space. So I'm going to kind of rotate it and flatten it. We'll add in the z-axis, and then we'll figure out what the innermost bounds are telling us about our z-coordinates across our domain of integration. So first, let me set up our picture. Now I'm going to take our picture and essentially flatten it and sketch it as part of the XYZ space, R3. So here's our y-axis, and I'm only going to draw the positive x-axis. Now, I'm drawing this at an angle. You have to imagine you're kind of looking at R3 from an angle. So here's the positive x-axis and the positive y side. Now let me put our semicircle. It's not going to be a great looking semicircle compared to the one on the right. Oh, that's okay. Communicates the idea. So here's our shadow in the xy plane. Now this shadow is not necessarily part of the domain of integration. Rather, if you imagine that the sun is shining directly down from the positive z-axis, so it's directly overhead, this is the shadow that our domain of integration would cast down on the xy plane. Z goes from the square root of x squared plus y squared up through r. So our z values are only above the xy plane. So I'm just going to drop in the positive z-axis like this. So as we travel upwards, we enter the domain of integration along the surface which is described as z equals the square root of x squared plus y squared. And we travel up, 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 and we exit out of the plane z equals r. So z equals x squared plus y squared, you can work out manually what that looks like, but it's one of our quadric surfaces. So this is the upper cone. So let me add that into our picture. I'm not going to incorporate the upper bound yet. I'm just going to sketch the idea of the cone. Okay, that's not a great looking cone, but imagine that that's the upper cone. So we enter the domain on the cone and then we exit out through z equals r. That means we want to understand the intersection of z equals r and z equals x squared plus y squared. Those two intersect when they are both simultaneously true, which means z equals r and z equals the square root of x squared plus y squared. So r equals the square root of x squared plus y squared. Or in other words, x squared plus y squared equals r squared. So in terms of the x and y coordinates, it's part of the circle of radius r. That's going to sit directly over this portion of the circle of radius r that we sketched in the xy plane. So because I have the ability to do so, I'm going to kind of copy paste that circle here. Now let me clean up this picture a bit. So we enter the region on the cone and then we exit through the plane z equals r. So this is the solid cone, or solid half cone of height r. Okay, so this solid half cone is our domain of integration. We now need to describe the solid half cone with spherical coordinates. Since we now have our domain of integration, I think I can get rid of everything and just keep this picture. So let me do this on a new slide. Okay, for spherical coordinates, we need to determine bounds for three quantities. One is the angle theta that we rotate through in the xy plane. That's actually going to be probably the easiest one in this example problem. Another one is the radial coordinate we typically call rho, which measures the distance the points in our domain of integration make with the origin. And then the third one is the angle phi that we make as we rotate downwards from the positive z-axis. So the quickest one that I see is theta. Because we go from the negative y-axis up through the positive y-axis, our theta bounds are going to go from negative pi over 2 to pi over 2. The next one I see is phi, the angle we make with the positive z-axis. Some of our points are right up against the z-axis, so that's a phi value of 0. And then we rotate down, 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 out to the edge of the cone. So if we go along the a YZ plane, if you will, we're like down, 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 down. So we're making an angle with the z-axis, and then we stop on the edge of our cone. So for phi, we're going to have 0 is less than or equal to phi is less than or equal to the phi value that points on the cone make. To figure that out, let's take the cone equation and translate it into spherical coordinates. So our cone equation started out as z equals the square root of x squared plus y squared. In spherical coordinates, z is rho cosine phi. I will do the whole x squared plus y squared computation in full detail, but that's something that you might kind of know about spherical coordinates once you've done it a couple times. X squared in spherical coordinates is rho squared cosine theta squared sine squared phi, like that, plus y squared is going to be rho squared sine squared theta sine squared phi. Now if we factor out rho squared sine squared phi from both terms, we would have rho squared sine squared phi times the quantity cosine squared theta plus sine squared theta. So that's going to give us the square root of rho squared sine squared phi, because it's rho squared sine squared phi times 1. The square root of a number squared is the absolute value of that number. So let me write absolute value of rho sine phi. So a lot of people think square root of x squared is x, but that's not really true. The square root of x squared is the absolute value of x. However, it so happens that rho is our distance to the origin, so that's positive. And then sine of phi is also positive. So this is actually rho sine phi. Okay, let me give myself a little bit more room so I can finish it all on this page. All right, so our equation for the cone in spherical coordinates has now turned into rho cosine phi equals rho sine phi, or in other words, cosine phi equals sine phi. You could divide over by cosine phi and write tan phi equals 1 if you want, or you can just look at this and say, what angle has the same sine and cosine value? We're above the xy plane, so our phi needs to be between 0 and pi over 2, so the answer is phi equals pi over 4. Okay, at this point you might have lost track of what we're doing, but we were trying to find the domain for phi. So now we can say that phi is between 0 and pi over 4. Let me just add that to our bounds down here. So 0 is less than or equal to phi is less than or equal to pi over 4. Okay, all that remains is to figure out rho. Rho is a radial coordinate. So to determine rho values, I like to start at the origin and draw rays kind of coming through my domain until they exit. So if we travel outwards from the origin, we do have a solid region of integration here that touches the origin. So that means the lower bound for rho is going to be 0. So we start here, and then rho increases away from 0. So increase, 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 increase. And then we exit the region here along that ray, or here, or here. If we go straight up, it's going to be here. These lengths are different. So this one is the shortest, this one is the longest. What's different about these three measurements is how far away we are from the z-axis. In other words, our rho coordinate is going to change as phi changes, as we kind of rotate away from the North Pole. I recommend drawing this region now from the side. So to figure out rho, I'm going to sketch a 2D picture here. What I'm going to do is point the positive y-axis right at my eye and sketch the xz plane. Essentially like this. So the y-axis is pointing straight at you, the positive y-axis. That makes this the positive x-axis and this the positive z-axis. So we're going to look at our region along this axis. This is pointing right at your eye. Viewed in this way, our region flattens into a triangle. And I can think of the rays that I drew out of the origin as cutting through this triangle now like this. In particular, we want to understand this length right here. So this side of what is now a right triangle, I'm going to label rho. That's really like our maximum value of rho. So as I travel along this line segment, we start at rho equals 0 and we max out here. This is the angle phi that we're opening up with the positive z-axis. And then this side length on the right we know is r. I could start trying to fill in other pieces of information about this triangle, but this is all I need. Because with this angle, this adjacent side, and this hypotenuse, I can write down a cosine statement. So in particular, cosine phi equals adjacent over hypotenuse. So that tells me that the maximum value of rho is a function of phi. It's r over cosine phi. Or if you prefer, you could write r secant phi. Okay, so our third set of inequalities is going to be 0 is less than or equal to the radial coordinate rho is less than or equal to r divided by cosine phi. I have a preference for sine, cosine, and tangent rather than secant, cosecant, cotangent, so I'm going to write that. Okay, we've done a lot of the work now we can set up this triple integral in spherical coordinates and then finish it if we evaluate all the way to the end. This might be all you wanted to see, but if you'd like to see this completed, let's keep going. Okay, so let's erase this side profile. We can now say that this triple integral is going to equal the integral from negative pi over 2 through pi over 2 for theta, and then I have to have rho before phi because rho depends on phi. So my middle bounds will be from 0 to pi over 4. That's for phi. And then for rho, it's going to be from 0 to r divided by cosine phi. Overall, these are much nicer bounds than what we started with. So here we had two bounds which had expressions that depended on other variables. They were square roots. In this new scenario, two of our bounds are constants. That's kind of ideal. And then the inner one is not too complicated. X in spherical coordinates is rho cosine theta sine phi. And then we need to remember to include our conversion factor. So that's going to be rho squared sine phi. And then the way I've ordered these, d rho, d phi, d theta. All right, I don't think this is going to be a great integral to do, but let's go ahead and see what happens if we integrate from negative pi over 2 to pi over 2. And then from 0 through pi over 4. Now let me start combining my trig terms, and I'm going to go ahead and anti-differentiate rho cubed. So we have cosine theta, sine squared phi, and then the antiderivative of rho cubed is 1/4 rho to the 4th power from 0 to r divided by cosine phi, d phi, d theta. All right, I'm going to pull the 1/4 in front of everything. Theta and phi are independent. I'm going to pull that out too, just so I'm looking at less. And then let me give myself some more room by erasing this. So it's 1/4 the integral from negative pi over 2 to pi over 2 cosine theta d theta. In fact, I'm going to go ahead and split this into the product of two integrals since both bounds are constant. So it's going to be the integral from negative pi over 2 to pi over 2 of cosine theta d theta times the single integral from 0 to pi over 4 sine squared phi over cosine to the 4th phi d phi. Okay. Oh, wait a second. I've lost my r dependence. Oh, we were supposed to have r to the 4th. So let me put that in front here. Okay, so the r to the 4th I've pulled out with the 1/4. Okay, let's keep going. I'm going to rewrite this now as r to the 4th divided by 4. Antiderivative of cosine is sine, so sine of theta going from negative pi over 2 to pi over 2. It's a nice computation. And then the integral from 0 to pi over 4. Sine squared over cosine to the 4th is sine squared over cosine squared times 1 over cosine squared. So that's tan squared phi secant squared phi d phi. We have one more integral to evaluate, and to do that we can use u substitution, because if u is tangent phi, then we can replace du with secant squared phi d phi. We'll need to change our bounds too, but let's do that on a new page. Okay, so we're almost done. We have r to the 4th divided by 4. Sine of pi over 2 is 1, minus sine of negative pi over 2 is negative 1. And then lastly, tangent squared phi we'll write as u squared, and then secant squared phi d phi is du. To change our bounds, we'll realize that when phi is 0, u is tangent of 0, which is 0. And when phi is pi over 4, u is tangent of pi over 4, which is 1. So we'll have r to the 4th divided by 4 times 2 times 1/3 u cubed, evaluated at 0 and 1. So overall, looks like r to the 4th divided by 6. Okay, I hope you enjoyed this demonstration of taking an integral, sketching its domain of integration, describing that domain of integration using spherical coordinates, and then integrating. Thank you for your attention.